When we were solving equations, we talked about using the distributive property. We only did it with numbers. We're going to add in a couple extra things to this video. We're going to look at doing the distributive property with variables. We're also going to use double distribution in a little bit. For all of these examples, I'm going to start out looking at an area model though. So let's say we had a rectangle, and this particular rectangle had a side of x and a side of x plus 5. If we wanted to find the area of this rectangle, we could look at each little rectangle. The first rectangle is x times x, which is x squared. The second rectangle is x times 5, which is 5x. So we could say that the area of this whole rectangle was x squared plus 5x. You don't always need an area model to actually do these type of problems though. This is x times the long side, which is x plus 5. By the distributive property, we can just multiply everything inside the parentheses by that x outside. So we end up with x squared plus 5x. Same thing. If we had x times x minus 4, we could draw an area model to represent this. This would be a rectangle that has two parts. It has x and a minus 4 on the long side, and then it has an x on the short side. If we did this with our area model, we would end up with x squared here and negative 4x here. So we could say that the area of the whole rectangle was x squared minus 4x. If you didn't want to actually draw out the whole rectangle, you could use the distributive property without it. X times x minus 4. And when we use the distributive property, we just multiply everything inside the parentheses by the thing, or the number, the variable, whatever is outside the parentheses. So we end up with x squared minus 4x. So here's another one that can be done both ways. If we wanted to use an area model, we could label the short side as the 3x, the thing that's alone. The long side is split in two, and we would have 2x and minus 5. The area of the first one, that would be 3x times 2x, which is 6x squared. The area of the second rectangle is 3x times negative 5, which is negative 15x. When we add these together, we get 6x squared minus 15x. Again, you didn't need an area model to do this if you just wanted to use the distributive property. 3x times 2x is 6, and then x times x, x squared. 3x times negative 5, negative 15x. Same thing. This works even when you have more than one variable in. So if you had, let's say, x squared y times x plus y, you can still draw an area model for this. This is still a rectangle with two parts. X squared y is outside, and then the long side is x and y. Again, we just multiply the two sides to find the area of the first one. X squared y times x. We need to remember this from our properties of exponents. X squared times x is x cubed, and the y just comes along because he has nobody else in this case. Now when we find the area of the second little rectangle, we have x squared y times y. We get x squared, y squared, based on our properties of exponents. When we add these two things together, we get x cubed y plus x squared y squared. Now I can't add those together any further because they are not like terms. And remember, like terms are things that have exactly the same variables and exactly the same exponents. In this case, the exponents are not exactly the same, so I cannot add them. If you wanted to do this problem without the area model, you would just distribute. X squared y times x, which is x cubed y. X squared y times y, which is x squared y squared. Got the same thing in either case. So what if we had three things inside the parentheses? We can still use an area model for this. This rectangle would actually have three parts to it though. we would have 5x on one side, and then our rectangle would need to be split into 3 parts. 3x squared represents 1, 2x represents another, and 1 represents the last one. Using the area model, just find the area of all 3 rectangles. The first one is 15x cubed. The second one, negative 10x squared. And the third one, 5x times 1, is just 5x. So when you put these all together, you end up with 15x cubed minus 10x squared plus 5x. We cannot add those together because the variables and the exponents are not exactly the same, so that's our final answer. If you were to do this without the area model, you would just distribute into each of those 3 things. So we would get 15x cubed minus 10x plus 5x. For this last single distribution example, I'm not actually going to draw an area model. I'm just going to distribute because there's a lot of stuff going on. First set of parentheses that I need to distribute with is with that 4x. So I need to do 4x times 3x squared. 4 times 3 is 12. X times x squared is x cubed. Then let's do the second part. 4x times negative 5, which is negative 20x. Now in our second parentheses, we're distributing not just the 3, we're distributing the whole thing. We're distributing the negative 3. So we're going to distribute negative 3 to all of the terms inside the parentheses. So negative 3 times 4x cubed is negative 12x cubed. Negative 3 times negative 5x is positive 15x. And negative 3 times 1 is negative 3. Now, we need to combine like terms in this case because I see some things that have the exact same variables and the exact same exponents. I have 12x cubed minus 12x cubed. Well, in this case, those are opposites, so they actually cancel out. All right, that makes my answer a little bit easier. I also have negative 20x, and I have positive 15x. Negative 20 plus 15 is negative 5x. Then I have a negative 3, and he doesn't have any like terms, so he stays as he is. So the final solution of this big single distribution problem is negative 5x minus 3. So we looked at using area models to do single distribution. Now we're going to step it up a notch. We're going to make some bigger rectangles and use some area models for double distribution. Double distribution would happen if instead of just one thing in front of the set of parentheses, you had 2 parentheses that each had 2 parts. So these are 2 different factors. We have x plus 2 times x plus 3. Let's make an area model for this. This area model needs to be split into 4 parts because each side of the rectangle has 2 parts to it. I have x and I have 2, and then the other side of the rectangle is x and 3. Now let's use that area model method from before. We need to find the areas of all the smaller rectangles. X times x is x squared. X times 3 is 3x. Okay, now on to the bottom. 2 times x is 2x. 2 times 3 is 6. Now let's finalize our problem by combining like terms. If you notice, these guys are exactly the same. I have 2 x's and 3 x's. Altogether, I have 5 x's. So our final answer is x squared plus 5x plus 6. Just like with single distribution, double distribution can be done without the area model. This just means that we have to distribute twice. I'm going to distribute with the x, and then I'm going to distribute with the 2. So let's start with the x. The first arrow I drew was x to x. So x times x is x squared. Then I did x times 3, so that would be 3x. With the 2, we do 2 times x, which is 2x, and 2 times 3, which is 6. Just like before, I have a couple like terms there. I have 3x's and 2x's, so we need to combine those. So our final solution is x squared plus 5x plus 6. Same answer as we got when we were using our area model. So a lot of the things are similar from single distribution. It's just that you have a bigger rectangle, you have more things to look at. Here's another area model that would need 4 squares in it. So one side of our rectangle would be x and 1, and one side of our rectangle would be x and -2. Let's find the areas of each of those smaller rectangles. You get x squared, -2x, 1x, and -2. When you combine those like terms in the middle there, we'll end up with x squared minus 1x minus 2. That was using our area model method. We can also use our distribution, but we need to remember to double distribute. We need to distribute with both terms in the first parentheses. So we start out with x times x. We're going to get x squared. Then we're going to do x times -2 to get -2x. 1 times x, and we're going to get 1x. And 1 times -2, which is -2. Combine like terms in the middle, and you're going to end up with x squared minus x minus 2. Same thing we got with the area model. Now, what if we only had one term? What if we had x minus 2 all squared? It looks like it's only one term, but really it's two things. If you see that square, remember that just means write it twice. So this is x minus 2 times x minus 2. We can draw an area model for this one as well. Both edges of the rectangle are going to be x minus 2. We go about solving this the exact same way though. X times x, x times -2, -2 times x, and -2 times -2. Combine your like terms in the middle. You're going to end up with x squared minus 4x plus 4. Same thing would be true if we used our double distribution from the beginning. We could just say x squared minus 2x minus 2x plus 4. After you combine your like terms, you're going to end up with the exact same answer you did with the area model. X squared minus 4x plus 4. Let's do this one by using double distribution first. Let's go ahead and distribute that x. So we get x times x, x squared, minus 4x. I'm going to distribute the 4. 4 times x, and 4 times -4. So when we combine our like terms in the middle, we're going to end up with x squared, and those cancel out, minus 16. So what would the area model for this one look like? It would actually look exactly the same as the other area models we did. We would have an x and a 4 on one side, and we would have x and a -4 on the other. When we did all of our multiplication inside, we would see that we end up with the exact same answer as we did before after we combined these two. So it's still a rectangle, it's just that those parts of the area model cancel each other out. We can also look at things that aren't just x and x. So we could do x minus 3 times x, 6x, minus 2. This would have the same type of area model, would follow the same rules of double distribution. One side would be x minus 3, and one side would be 6x minus 2. When you multiply each of those things out, we have x times 6x, so we get 6x squared. Using double distribution, x times 6x is the first thing we do there. Now we need to do x times -2. If you look at the area model, x times -2 comes next as well. So we get -2x. Okay, now in the bottom of our rectangle, we have negative 3 times 6x. So we get negative 18x in both cases. And then we have negative 3 times negative 2 in both cases, which is positive 6. Combine like terms. Your like terms are usually always in the middle. You're going to end up with 6x squared minus 20x plus 6. Exactly the same thing you would get with the area model. So even with that extra coefficient in there, nothing changed. We're still using the same procedure to carry out our double distribution. I'm going to do this one without an area model. If you want to draw an area model, that's fine. But we're going to do the same steps either way, whether you just use your double distribution or whether you draw an area model. This one has lots of variables in it, but we're still just going to be using the same principle. 6x times 6x is 36x squared. 6x times y is just 6xy. None of the exponents change because x and y are different. When we distribute our negative y, we're going to end up with negative 6xy, and we're going to end up with negative y squared. I actually have a couple of like terms here in the middle. I have 6xy and negative 6xy, which are actually opposites, so conveniently enough they cancel each other out. And our final answer is 6x squared minus y squared. We could draw a rectangle for this one as well. We would label our rectangle just like we did before, and we would end up with this same answer. And another one let's do without an area model. Let's do 4p minus 1 all squared. Remember what it means to have that all squared thing. That really just means it's 4p minus 1 twice. Now you can use double distribution because we have it written in our way, so we can draw all our arrows. I always draw my arrows so I remember that I did all 4 multiplication problems. 4p times 4p is 16p squared. 4p times negative 1 is negative 4p. Negative 1 times 4p is negative 4p. And negative 1 times negative 1 is positive 1. Now, don't be fooled in this one. If you look at those middle terms, they're not opposites. They actually get combined. Negative 4 and negative 4 is negative 8. So our final answer is 16p squared minus 8p plus 1. The last 2 examples we're going to look at are sort of our challenge problems. Again, they could be done using area models, or they could be done just using double distribution. In this case, I'm just going to use double distribution. In the first set of parentheses, I have an x, and so I would do my little arrows as usual. But in the second set of parentheses, I have 3 things. This doesn't change our method. It just means we have another multiplication problem to do. So x needs to get multiplied by all 3 of those things. X times x squared is x cubed. X times negative 2x is negative 2x squared. And x times 3 is positive 3x. Now I'm going to do the second part, the 5. And the 5 needs to go with all 3 things. So we're going to end up with 5x squared minus 10x plus 15. Now we need to combine like terms. X cubed. No other x cubed, so that stays x cubed. X squared. I have a couple x squared, so these need to get combined. We end up with 3x squared. X's, I have 3x and negative 10x, so I have negative 7x's. And 15 is the only number, so it stays like it is. And that's our final answer. We did not do anything different. We just drew an extra set of arrows. We still use double distribution. In this case, we can't simplify this any further because the exponents on those x's are all a little bit different. We've combined all the like terms that we could. On this one, we actually probably couldn't do an area model very well for it because it has 3 things. We would have a cube here instead of just a rectangle. So if I were just to give you the first 2, let's ignore that third one. If I were just to give you the first 2, that's just a basic problem. That's a x times x x times negative 7 just using double distribution. So we would get x squared times negative 7x, and that would be plus 3x minus 21. Then we would combine our like terms, and we would say x squared minus 4x minus 21. And that's it for the first two. However, we still have that third one that we need to deal with. So I'm going to rewrite that one in front of this answer, x plus 1. Now, this should look familiar to you. This is a problem that we did on the last slide, where this one had the 3 arrows in it, but it was still double distribution. So we can do this problem just like we did the last one. X times x squared is x cubed. X times negative 4x is negative 4x squared. X times negative 21 is negative 21x. 1 times x squared is x squared. 1 times negative 4x is negative 4x. And 1 times negative 21 is negative 21. Now, I know you guys are all yelling, there's like terms, combine them, combine them. All right, I will. X squareds have like terms, and the x's have like terms. So when we finally combine everything, we're going to end up with x squared minus x cubed minus 3x squared minus 25x minus 21. And since none of these have common variables, that's our final answer. As I like to do, we are going to do a little recap. Our single distribution recap is when we have something like x times x plus 2. So we would have x squared plus 2x. Our area model just has 2 parts to it. We can also write this as x times x plus 2, and we can use our arrows to do our single distribution and arrive at the same solution. We also can have double distribution problems. That's where we would have a rectangle that has 4 parts in it. So x plus 3 and say x minus 4. We would see this written out as x plus 3 times x minus 4. This is double distribution. So single distribution, double distribution. We can do this in 2 ways as well. We can just distribute this way, or we can use our area model to find the areas of all the smaller rectangles. Whichever way works best for you. No matter what, we're going to arrive at the same solution. After combining our like terms, either in the middle of our double distribution or in the middle of our area model, for this problem, we'll end up with x squared minus x minus 12. So single distribution is when you have one thing in front of the set of parentheses. Double distribution is for when you have more than one set of parentheses.